Hey everyone, and welcome back to our electronics tutorial series. My name is Aaron from AX Electronic, and today we are going to continue talking about MOSFETs, except now we're going to talk about them in a different application. So before, we have used MOSFETs as high current switches, which we can use a very low voltage to control. And we've also talked about how we can actually implement logic circuits using MOSFETs. But now we're going to switch gears. So instead of working with digital switches or digital signals, things that are either on or off, we're going to move into the analog domain. So we're going to talk about how we can use these MOSFETs as amplifiers. So let's go ahead and jump right on into it. So an amplifier, if you remember, is just an electronic device used to increase the amplitude of electrical signals, okay? So an electronic device used to increase the amplitude of electrical signals. So what does this mean? Well, in a lot of instances, you might have a really small signal. So let's say that you play electric guitar, and that electric guitar outputs a signal that is this big. Not very big, right? And if you fed this directly into your speaker, it'd be really small. So if you went to something like a concert and you could only hear a really small electric guitar, that wouldn't be too good. So what they do is that they will put this signal through an amplifier, and that will amplify it to be really loud, okay? But important things about amplifiers is that we want to pretty much multiply this signal. So we don't want to distort this signal too much. We only want it to get bigger. Okay, so we only want it to get bigger. We don't want to distort it. We don't want it to have any clipping, things like that. So that's all pretty important whenever it comes to amplifier design. Now, we do know how to make an amplifier using op amps, but op amps, even though we said that they're ideal, only work up to a certain frequency. So we initially said that op amps, these two inputs have no current flow into them at all. But once you get to higher frequencies, that stops being true. So there's some capacitance, there's some impedances here that you'll see at higher frequencies, and that'll actually start to load down your input, change your analysis, and then that'll actually make it to where these op amps don't work as amplifiers anymore. They're not giving you any sort of gain. So whenever that starts happening, you have to use these MOSFETs, or you have to use these transistors to start making your own amplifiers. So this is especially important at high frequency amplification, that we can use these transistors to make amplifiers. Now MOSFETs are one option. We're going to talk about another type of transistor that you may end up wanting to use more for amplifiers, but MOSFETs definitely are one option, okay? So we need to talk a little bit about the vocabulary for these MOSFETs, okay? Because these MOSFETs, they might have a little bit different terms that we haven't heard before, so I just want to make sure that we are reviewed and that we understand what's happening here. So DC bias is the first one that I want to take a look at. So DC bias, this is going to be the level at which an amplifier operates. So if you just consider a MOSFET, if we tried to feed a really small signal into a MOSFET, this thing would never turn on. So if this thing were only 1 millivolt, we would never turn that MOSFET on. We'd never get anything on the output at all. So we have to use a DC bias to get this MOSFET turned on already into a specific operation region. And whenever we do that, now our small signals can actually create pretty large changes at the output. Okay, so we need that DC bias to kind of set the stage for our small signals to actually be amplified. Now transconductance is another one that you may have never heard before. And you might hear me talk about GM, or I might do G little m, and this is going to be our transconductance. So what this is that this is a property of the MOSFET. So if you remember, we have a MOSFET, and we have a graph that relates our gate source voltage to the amount of current flowing through the drain, or flowing through the whole MOSFET. So what GM tells us is that tells us that for a little change in current, how much change in VGS do we need? Okay, so this is going to tell us what a little tiny change in VGS is going to do to our output. Okay, now this does depend on where we are operating at. So if you remember, we might have something that looks like this. If this is our VGS down here on the bottom, and this is our ID, here this graph looks really linear. So our GM might be a constant, something like 20. But over here, it starts to taper off. So now it does still look a little bit linear, but its slope is a lot smaller. So for a big change in VGS, we might only get a little change in current. So GM might only be something like 0.2. Okay, so transconductance in GM does change depending on where you are working this amplifier. Okay, and that's something that we're going to have to remember. Now, small signal gain is the last thing I want to talk about. So voltage out versus voltage in. So you may have seen before AV is equal to V out over V in. That's just our small signal gain. Now, small signal tells us something that is actually pretty important. So like I said before, we have to work these amplifiers in specific regions. So if I have just a little tiny VGS, I'm working in a very small region on this graph, okay? And it's mostly linear, okay? So if we take a look at the ID, it's going to look proportional to that input. So let's switch this up now. So instead of working at this level, let's assume that we have a really big signal and we're working over here, okay? So now we're working over here. Our signal is very, very large. And this doesn't look as linear now. So what we're going to see is that since this doesn't look as linear, our output current isn't going to look the same. So it might look something like this. So you might get some nonlinearity, some distortions, it could be clipping, things like that, which is generally not good for your amplifier, okay? So this is something that you have to consider, is that these amplifiers are built around smaller signals. You can accommodate a larger signal, but you're going to have to change your analysis. It becomes a little bit more complicated. But we're not going to concern ourselves with that because we're only going to be concerned with small signals for this lesson, okay? So now we've got the amplifier out of the way. Let's talk a little bit about DC biasing, okay? So this is a general way that we can DC bias a MOSFET. So remember, this is our gate, our source, and our drain. Now, we have to turn the FET on before we can do anything with it. So like I said before, if we put a 1 millivolt signal into the gate with no DC bias, that transistor is never going to turn on. So we're not going to get anything on our output. So because of that, we're going to bias this MOSFET. Now, our MOSFET will start conducting current whenever we have a positive voltage on the gate to source. So what we can do is that because there's no current flowing into this gate, the only path for the current in this instance is through these resistors. So this is just a simple voltage divider. So if we call this one RG1, or excuse me, RG2, and this one at the top, RG1, we can set our gate voltage very easily. So we can set our gate voltage super, super easily using these two resistors here. And because there's no current flowing, it makes it very simple. Now, this VGS is going to kind of determine our operation region. And what you'll see is that we have to make some assumptions in the very beginning. Okay, so we have to take some liberties as designers whenever we're designing these circuits, and then maybe come back, tweak things later on once we get a little bit bigger picture of how it works. Okay. So once we set this gate voltage, this is actually going to set this is going to set the current through this MOSFET, okay? So this is going to set the current through this MOSFET. Now, we also have this source resistor here, and the reason that we have that is because that actually provides a little bit of stability, okay? And if you dig down, you can actually look at something called load lines, and that'll give you a little bit more information on this stability and how this source resistor provides it, but generally it's going to be something that you want. So we might account for a 1 volt signal here. And if we know the current, if we assume in this case it's 10 milliamps, we can calculate this resistor based on Ohm's law. So just V over I. So if we do 1 volt over our 10 milliamps, that'll give us our source resistance. Same thing up here at the top. So what we're going to see is that whenever we have this signal on our output, we want to make sure that it has as much room as possible. And in order to do that, we are going to pick this point, our VD, very carefully, okay? So our VD is going to be picked very carefully, so that means we're also going to have to pick our RD based on our VDD, our VDD minus VD over, ID, not RD, so ID. And that's going to let us pick that drain resistor, okay? So this is just a very basic example of DC bias. Now, we're going to actually switch gears and move into the small signal model. So before we were looking at only DC. A small signal model, you can think of it as an AC model, okay? So we're going to assume that DC sources are not there. So if we have a DC voltage source, it's just a short to ground, okay? So that means that over here, we're going to have a path to ground. We're also going to have a path to ground on our source and through our gate, okay? But they're all going to be different. We'll look at it in more detail here in a second. So this is the ideal model for a MOSFET. So we don't have any current flowing from our gate to our source. And we have a variable drain current. So this is ID. And this is our drain up here. So we have a variable drain current based on VGS. And you'll see that this VGS is multiplied by GM, which is what we said earlier is our transconductance. Now, this is only going to work for smaller signals because as we get larger, it's not going to have this really pretty nice relationship. But for small signals, this works really, really well. So this is called the hybrid pi model. And there's definitely different models out there, but I like the hybrid pi, especially because as you move into more detail, maybe move into higher frequency, this one is going to be really, really good for these designs, okay? So let me move my notes down a little bit. So like we said, this gate is like an open circuit. No current is going to be able to flow through this gate to anywhere else. So IG is going to be 0 because it's just an open circuit. And then we have this variable drain current, okay? So if we suppose that we have a GM of 20, let's see. So if we have this GM of 20, and we have a VGS, something like 1 volt. So if our VGS is equal to 1 volt, then we're going to end up getting 20 amps on the output, okay? So that is how this is going to kind of relate our gate, which is our input, to our output, which is our drain, okay? So that GM is going to be pretty important, okay? So what we're going to do is that we are going to derive a common source amplifier, okay? We're only going to focus on common source because I think it's the simplest to understand and also probably the most common. So we're only going to focus on common source. Now, we're going to assume, for this case, we're going to start off with our AC analysis, okay? Or our small signal analysis. So you'll see that I don't have these gate resistors here, okay? So I don't have these gate resistors. So what we're going to assume is that these gate resistors are large enough to where they're not really going to take a whole lot of current from this supply, okay? So we're just going to assume that it's like they're not even there. Okay, so that's just going to make it a little bit easier on us in the future. So now, this is our Vn, and we can see that our Vn is just equal to this Vg, okay? So we have this hybrid pi model set up. So this is how it looks in an actual schematic, and this is how we're going to model it with that hybrid pi model. So our small signal model versus our actual design, okay? So let's derive a little bit more about this common source amplifier, okay? So we know that we have Vn right here. So if this is our Vn, we know that Vn is equal to our gate voltage. And we also know that this is our source. Let me make sure I'm clear here. This is our drain, okay? So if we want to know VGS, we have to calculate our gate voltage and subtract our source voltage, okay? Because that's the definition of VGS. So we know our gate voltage already, but we don't know our source voltage. So to figure that out, what we're going to do is that we are going to just start tracing from ground until we get to our source, and it's going to be really easy, okay? So I'm going to label a couple of things first. So this is that was our RS, this is our RD, and we have a current source here that is pushing current through this path. There's no other path for it to go. So this is going to call, I'm going to call ID, and ID is that GM VGS, okay? Now, VS is what we're trying to find right now. So we know that VS is, let's see, so our VS is going to be 0 volts because that's where we're starting. And if we trace a path through this resistor, we're already at our source. And the voltage drop across that resistor is pretty easy, okay? So we know that it's going to be 0 volts plus RS times ID. And the reason it's plus is because of the direction of the current and what I'm defining as the voltage drop, okay? So because the direction of the current is this way, that means that we actually have a rise from here to there, okay? So voltage is dropping from top to bottom or rising from bottom to top, okay? Now, don't need to get rid of that. So I'm just going to call this RSID. Now we know ID is equal to GM VGS. So that means we know that our VS is equal to RS GM VGS. Now we can calculate our actual VGS up here. So remember, we started off by saying VGS is equal to VG minus VS. We know VG is VN, and then minus VS. So VS is RS GM VGS. Alrighty. So this is our equation for VGS, and we can actually rearrange because we want to get Vn by itself. Okay, so we want to get Vn equals something, V out equals something, and then put those on top of each other to get our gain. That is our goal, okay? So let's try not to lose sight of that goal, okay? So we need to get Vn by itself. The way we can do that is just if we move this to the other side. So we'll end up getting Vn. And I'm going to go ahead and skip a step here and factor out this VGS. So we get VGS times 1 plus GM, not VGS, RS. So that is our input voltage, okay? So we have input voltage is equal to VGS times 1 plus GM RS, okay? So this is a pretty good expression for our input voltage, okay? Because it has this VGS, we think maybe we can factor it out later, and then we only have these two physical parameters, okay? Now let's try and do the same thing for V out. So our V out is the same as our drain voltage, right? So our V out is our drain voltage. And if we consider that our current is going this way, if we follow the path of our current, we're going to start from 0. Okay, so our V out is going to be 0 volts. And now we're actually dropping. So it's going to be minus RD ID. So let's just say it's minus RD. And then ID, remember, is GM VGS. And this is our V out, okay? So that's our VO. Let me make sure I'm clear about that. That's VO. So now our last step is just to set V out over V in. And our V out is minus RD GM VGS. And our V in, it's this big long thing at the bottom. So it's VGS, open parentheses, 1 plus GM RS, okay? And we can factor out this VGS. And what we get is that our gain, our AV, our small signal gain, is going to be minus GM RD over 1 plus GM RS. All right, so that is our small signal gain. Now, if we want to have maximum gain, what we need to have is we need to have a really big RD, or a really big drain resistance, and we also need to have a really small source resistance. So ideally, we would have that 0 ohm source resistance. But we like having that source resistor there because it does provide us a little bit of stability. So we'll talk about maybe how we can do some cool engineering tricks in order to kind of get a nice trade-off. So just remember, as we increase RS, we're decreasing our gain. As we increase RD, we're increasing our gain. Now, the trick with RD is that as we increase RD, we're only going to be able to provide less current, and that might actually reduce our GM enough, or our transconductance, to where we're not actually increasing our gain. Okay, so this might be something pretty important that you need to consider, okay? Now, let's move on to the next slide, and we're going to start talking about a practical design, okay? I want to go back real quick, though, and just mention that if we take a look at this AV here, we have a negative value, okay? So we have this negative value. And if you think about it, that actually makes quite a bit of sense, okay? Because if we add, let's say that we have an increasing voltage on our input, okay? That's going to cause an increasing current to flow, right? So this current is going to be increasing. So it's going to start increasing the amount of current flowing down, okay? So more current is going to flow down. That means that there's going to be more of a voltage drop. So if we started off at this level here and there's more of a voltage drop, we're going to be going down, okay? So as our gate voltage goes up, our drain voltage goes down, okay? So if we have a sinusoid, it's going to be flipped like that. So this is actually inverting our input signal, okay? Now, for our practical design, what we're going to do is that we're going to actually use a real FET, okay? So I'm going to use a real FET, and I'm not going to actually make this circuit in front of you, but what I am going to do is I'm going to switch to LT Spice at the very end just to see how we did in our simulations, okay? And also give you a little bit of a hint on how to simulate it. So the real FET that I'm going to use is the IRFZ 44N PBF. Okay, and I'm going to erase that, get it out of the way here in a second. But that is the FET that I'm going to be using, and I've pulled this information directly from the data sheet that I'm going to be telling you. Okay, so first thing, let's list what we know. Well, I'm going to constrain myself and say that we're going to use a 10 volt supply. So 10 volts is our VDD. Now, the data sheet tells us that the GM is equal to 19 at a certain current, so at a 25 amp drain current. So whenever ID is equal to 25 amps, our GM is 19. Now usually if we run these MOSFETs hotter, or if we run more current through them, we are going to get a higher GM. But in this case, that is a whole lot of current. So we don't want to have to provide 25 amps, because if we think about it, 25 amps times 10 volts for our supply, it's 250 watts. So that is a lot of power that's going to be consumed, and that's not very good. So what we're going to do is that we are going to assume that we're going to design our ID to be at 100 milliamps. So we're going to say our DC bias, there's going to be 100 milliamps flowing from the drain to source in this MOSFET. And because I did a little bit of simulation and peeked ahead, we can see that our GM is about 1.2 in this case. So our GM is 1.2 at an ID of 100 milliamps, okay? So we're going to use this information. Now, for 100 milliamps, we need a VGS that's just barely over the threshold, because if you remember from this graph, whenever our VGS gets above that threshold, we start to increase quite a bit. So if we're just 1 volt over that threshold, we could already be pushing 1 amp. So our VGS just needs to be a little bit over that threshold. So you can approximate it to be maybe right at that threshold. So I'm just going to use 4 volts here. So I'm going to assume that I want 4 volts as our VGS. I'll write it over here. We want our VGS to be equal to 4 volts. And all of this I'm just getting from the data sheet, okay? So I know that the threshold voltage is about 4 volts, so I'm going to assume that I want a VGS right at about 4 volts, okay? Now let's also assume that we want 1 volt on our source pin here, okay? So we have 1 volt on this source pin here. Remember, this source resistor is providing us stability, okay? So it's providing us a little bit of stability, so it's actually pretty important. So having that source resistor is important, and we do need to include it. So if we have 1 volt on our source, that means we're going to need 5 volts on our gate in order to keep a VGS of 4 volts. Right, so let's start off by trying to get 5 volts here. So if we have a VDD as 10 volts, and we want to get 5 volts here, it's just a simple voltage divider. So we can use something like a 10K and a 10K resistor to get that 5 volts on our input. But in the simulation, I ended up using 6K. So let's just use 6K to keep everything consistent, okay? Now, if we want 100 milliamps flowing through this resistor down here on the bottom and 1 volt, that gives us enough information to pick out RS. So RS is going to be our volt divided by our current. So that's going to be 1 volt divided by 0.1 amps, 10 ohms. So we know that RS is equal to 10 ohms, okay? So our RS is going to be 10 ohms. Make sure that I'm not going crazy here, checking my notes. So our RS is going to be 10 ohms, and I've listed it down here. Now, we need to pick out what we want our drain voltage to be, okay? Because we're the designers. We get a little bit of a choice as to what we want this drain voltage to be, okay? Now, what we need to do is that we need to actually look at our curves in our data sheet. And what we see is that for 100 milliamps, if our VDS, if our VGS is equal to, let's say VGS is equal to 4 volts, let's assume that we have all this information. If our VDS gets below about 2 volts, what's going to happen is that whenever we increase our VGS, we're going to be decreasing our VDS, and that's actually going to cause second order effects to happen. So our VDS and our VGS are both going to be impacting our output, which is not good. So that's going to cause a lot of wonky things to happen. So we need to make sure that our VDS stays at least 2 volts, okay? So we need our VDS to at least be 2 volts, okay? Oh, excuse me, sorry. So we need our VDS to at least be 1 volt, okay? So we need to make sure that the drop across the MOSFET is at least 1 volt. In order to make that happen, that means the smallest value we can get on our drain is 2 volts. Now, if we pick 2 volts to be our drain voltage, that may work only slightly though, because what happens is that if we try and go below 2 volts, we're going to get these weird effects down here, okay? So maybe it's going to look something like this instead of our sinusoid. So what we need to do is that we need to pick for maximum headroom, okay? So we're limited on the lower side to 2 volts. On the upper side, we're limited to about 10 volts, okay? So about our supply. So we have 2 volts on the bottom, 10 volts on the top. The best way to pick our drain voltage is going to be to average those together, okay? So pick the one that's right in the middle. So that is actually going to be 6 volts here. So we have 4 volts before we reach our top and 4 volts before we reach our minimum. So that's going to give us the maximum range to operate, okay? So we're going to pick 6 volts as our drain voltage. Now, once again, we know that this current is 100 milliamps flowing through this drain resistor here. We know that we're dropping 4 volts across it. So because of that, we know that this has to be 40 ohms. All right, so now we have set our DC bias to be exactly what it is that we want, okay? So let me erase some of this extra information here, okay? So we know that we have, 1 volt right here, 6 volts on our drain, and that we are pushing 100 milliamps through. Our source resistor is 10 ohms, get rid of that, and our drain resistor is 40 ohms. Now we can start switching into small signal, okay? So let me move over, okay? So we can start switching into our small signal design. Now, for our small signal, we are going to again have this hybrid pi, okay? So let me actually move back a little bit. So if I move back, we actually already derived our gain for the case where we have a drain and a source resistor, which is our common source amplifier, which is exactly what we have right now. So if I were to convert this into our hybrid pi model, the only thing that we would have is that we would have 2 extra resistors here tied to ground. because remember, those resistors being tied to ground is because they only have a DC level. So we're only looking at AC analysis. So this DC level up here is the same as an AC ground, okay, which is why they are both tied to ground here. But we still have a path for VN directly to VG. So this is not going to impact us too much. So we can use these same equations that we derived here, namely our gain. So let's plug in this value for gain. So let's say that our AV, and remember it's minus GM RD over 1 plus GM RS. And let's plug in what we know. So we know our GM is 1.2, so minus GM 1.2 times 40 over 1 plus 1.2 times 10. Okay, and let's see, that ends up being, what does that end up being? So that's going to end up being 48 over 13. Okay, so we're getting a gain of about 4. We'll just say that this gain is about 4. It's actually 3.7. Now, is this very much gain? Might be for your application, but in most cases, this is actually not enough gain. If we want an amplifier, we want it to amplify. So if we want to get an amplification of 10, we don't want to have to put 2 of these guys back to back, okay? So let's kind of take a look and see what it is that is causing us to get this bad gain. Well, this source resistance on the bottom definitely isn't helping, okay? So this source resistance on the bottom is changing our gain from what it would be 48 originally, which is pretty high, all the way down to 3.7. So what we need is that we need a way to have this drain resistor present whenever we are looking at only DC. And then whenever we're looking at AC, we need that drain resistor to disappear. So we need it to maybe be a short circuit. And the way we can do that is using a pretty cool engineering trick. So we're going to use a component that at DC is an open circuit and in an AC starts looking like a short circuit. Do you have maybe some thoughts about what it is? Maybe some of the alarm bells in your head are going off. It's a capacitor. So if we add a capacitor right here, if I call this our source capacitor here. Oh, let me make sure I'm not erasing. So this is our source capacitor. We're going to have the exact same equations, okay? So at DC, this is pretty much not here. So we still have our 1 volt, 10 ohms, 40 ohms, 6 volts here, just populating this with information. This is 6K, 6K, and 5 volts DC. But now, if we look at the small signal information, okay, so if we look at the small signal information, now we have a capacitor across this resistor, okay? And this capacitor, as our frequency gets higher and higher, is going to start looking like a short circuit. So instead of having this resistor here, we're just going to have a short circuit to ground. Okay, so now what we've done is that we've made it to where if we're looking at DC, we have our source resistance. But if we're looking at AC, that source resistance starts to disappear, okay? So now, So now we can plug in this same equation. So we have all these same DC values because this capacitor isn't here. But if we choose this capacitor to be large enough, like maybe 10 microfarads is good in most cases, then what we'll see is that our information for gain has changed. So we still have minus GMRD. And then on the bottom, we have 1 plus GMRS. Except now, RS looks like it's just a short circuit. So it looks like it's almost 0. Instead, we're just going to have 1. Okay? So now we're going to have 1 on the bottom, and that is going to give us our full gain of minus 48. Okay, so this is a whole lot better here, okay? So this is a good way of getting rid of the effects of that RS, really kind of taking down our gain. Now, we may want to have a variable gain too, right? Because you may not always want to have maximum gain. Maybe you want to have something in between. And the way that you can actually accomplish that is by using this sort of configuration, okay? So we still have our 6K and 6K. We want to have 5 volts here, 1 volt here, 6 volts here. This is 40 ohms. And now we have our 10 microfarad capacitor. We can actually split this 10 ohm resistance, okay? So let's say that we don't want the full 48. Let's say that maybe we only want a gain of 24. So we want our gain to be minus 24. Well, the way that we can do that is, remember, it is going to be minus GMRD, which we can't change, or we can't change in this instance, over 1 plus GMRS, okay? So this top is going to be minus 48, and we need GMRS to give us 1. Okay. Now, if we take a look in DC world, this capacitor isn't here, so we need these two resistors to add up to be 10. So they need to add up to equal 10. And if we look at AC world, this one is like a short circuit to ground. Okay, so it's like this resistor isn't even here. It's just a short circuit to ground. And what ends up happening is that we can pick this RS to be whatever it is that we want. So if we pick this RS to be, let's see, 1 over 1.2, or let's just make it 1 to make our lives easier. So we can make this 1 ohms. This is 9 ohms. In DC world, we have the same we have the same source resistance. Now in AC world, we're only seeing a 1 ohm resistor on the bottom. So we get minus 48 over 1 plus 1.2, and that's going to give us about minus 24. Okay, you should do the math a little bit better than I'm doing right now just to make sure you're getting it exactly right. But that's a good way of getting a nice variable gain if you don't need to either have full gain or small gain. Okay, so let me move down a little bit more. So let's look at a final MOSFET amplifier configuration. Okay, so let's look at this final configuration. Okay, so now the only thing that we've added in this case are these two capacitors here. So if we consider our AC source, okay, so this is providing our AC signal. We may not be able to take a DC level here because remember, here we have 5 volts. So if we try and apply an AC source here, it's going to short circuit that 5 volts. So a lot of current is going to flow and maybe our AC voltage can't take it, so it might break. So what we can do is that we can add these capacitors here. And what these capacitors do is that they block DC. So this DC level isn't going to be able to make it through, but at AC, which if this is high enough, like maybe 10 kilohertz, it's going to be able to pass directly through this capacitor. Okay, so our AC signal is going to make it directly to our gate, which is important. And kind of the same thing on the output. Remember, we have a DC level of 6 volts here, and we may not want that passed through to our load. So this will block it and make it to where our load only gets the AC level. Okay, so throwing these capacitors in here, again, 10 microfarads is a good value, is going to help isolate those DC signals. Now, the last thing that I want to talk about before we move into the LT Spice example is I want to talk about what happens if you have an actual load resistor here. So if we move back to the hybrid pi model, and let's just say I get rid of all this different stuff. Let's see if there's a good way to just clear all the annotations. So if we have our drain resistance here and our source resistance, if we have this capacitor, and say, for example, we have something like a load that we're driving, okay? So if we come to the very end, we have a load resistance. Maybe it's like 100 ohms or something like that. If we have this 100 ohm load resistance, here, this capacitor looks like a short circuit. In the AC world, it looks like a short circuit. So instead of having our gain is equal to minus GMRD over 1 plus GMRS, this RD is going to become minus GM RD parallel with RL, okay? So parallel with our load resistance. So that's something important to take into account, because if you know that you're going to have to drive a 100 ohm load, then you're going to have to take this into account whenever you're doing all this math, especially as it gets to be lower and lower resistance, because as it gets lower and lower resistance, it's going to load down your amplifier and make it to where your gain isn't as high. So you're going to have to really take that into consideration, okay? So enough of the talking and doing all this unfun math. Let's switch gears and let's actually look at an LT Spice simulation, okay? So let me bring my LT Spice simulation over here, and we can take a look at this simulation. So you can see that I tried to do as good a job as I can of transferring everything over from the schematic that we've done to this LT Spice simulation. So I've got this 10 ohm source resistor here in parallel with a 10 microfarad capacitor. I've got a 100 kilo ohm load resistance here with a 10 microfarad capacitor blocking that DC. Our 40 ohm drain resistor, 6K and 6K gate resistors. Now I have this, again, DC blocking capacitor here on our input. And if we take a look at this input voltage here, you can see we have a 10 volt supply. And if we take a look at our input voltage, what we have is that we initially have a 0 DC offset, an amplitude of 1 millivolts, and then a 100 kilohertz frequency. Okay, so this is going to be a pretty fast moving sine wave. And then you can also see that I have this little thing AC1 down here at the bottom. So if you remember from our AC circuit analysis examples, we can actually do some AC analysis. So it'll sweep across all different frequencies to kind of check how this amplifier is performing, okay? So I've got this all set up. I have this first SPICE directive commented out, so having that semicolon instead of the dot is going to make sure this is not run at all. So we're not going to run our AC simulation first. We're going to run our DC simulation. Okay, so let's go ahead and hit run and see what happens. So we're only running to 500 microseconds because this is a 100 kilohertz signal. It's moving pretty fast, okay? So we're only running to 500 microseconds. We're taking a pretty small step too, okay? So let's just make sure we're not crazy. Let's look at our input, okay? And you know what? I actually want to drop this, let's see. So I actually want to drop this simulation down a little bit. So it's going to get a little bit difficult to see that. Let's only do 250 microseconds, okay? So 250 microseconds, hit OK, and rerun. Okay, that looks a whole lot better for me to look at. So you can see that we have 1 millivolt peaks, so plus and minus 1 millivolts, and we're oscillating at 100 kilohertz. So that's where we're starting off at. We don't have any DC level on this component, but if we go past the capacitor, we can see that we still have this same 1 millivolt change, but now we have this 5 volt DC level added to it. Okay, so this has made sure that we are blocking that DC and then adding it in to this small signal high frequency signal. So that is going directly into the gate of our MOSFET. Now let's take a look at the drain, or let's take a look at the source of our MOSFET. Okay, so the source of our MOSFET, we do have some oscillations because, again, that drain current is shared between everything. So that drain current is shared between everything, so we're still going to see this on the output. We can see that it's at 946 millivolts or so. So it's at right about 1 volt, okay, which is what we designed for, which is good. So what we can see is that there is a pretty good amount of current that is flowing through this capacitor, okay? So there's some pretty high DC current flowing through our resistor, which is good. And we have some pretty high AC current flowing through our capacitor, okay? So that is making sure that we have our 1 volt here, but it's not going to reduce our gain by a drastic amount, okay? So now, again, we have 10 volts as our supply. This is our V out before the capacitor, okay? So we're oscillating at about 6 volts, okay? So we did a pretty good job at a first glance at this. So we're at about 6 volts. Maybe if we did a little bit more tuning, we could get it right where we need it to be. So we're right at about 6 volts. And now we are going from, well, let's just look at it whenever we don't have this DC level. So if we drop that DC level, now we're oscillating from like minus 48 to positive 48. Okay, so we're getting a good amount of gain here. So we're actually getting a good amount of gain here. And you'll notice that this 100K output resistance or load resistance is pretty large compared to our 40. So if we do 40 parallel with 100K, it's going to be right at about 40. So that didn't change our calculations too very much. So now what we can see is that we had a little tiny input voltage. So this is our input and our output. And we have it flipped because we have that negative. And now it's a whole lot larger. So we got a gain of about 48. Okay, so if we didn't want to look and maybe switch this to 10 kilohertz, megahertz, stuff like that, we can actually comment or re-comment in. So I'm going to get rid of that semicolon, change it to a dot, hit enter. And if I hit run, it's going to ask me which one I want to run. I want to run the AC analysis this time. So if I run our AC analysis, what we can see is that it is going to, if we probe our input, we are getting 0 dB. So that means that we're not getting any gain at all, which is good. That's actually exactly what we're expecting, because we made our AC level at 1 volt, and that means we're not going to be getting any gain at all. Now, if we take a look at this output, okay, so if we're looking only at the AC level on this output, you can see that at the low level of 1 hertz, we're actually getting reduced, okay? Because 1 hertz is low enough to where this all these capacitors are going to start looking like a pretty high resistance thing, okay? So they're going to start being pretty high resistance and start impacting our circuits, okay? And then we can get above 10 hertz and we get about 12 dB of gain, okay? So that 12 dB of gain means a voltage gain of about, let's see. So it'll be a voltage gain, well, it's still going to be pretty small, okay? So it's not going to be as large as what we actually wanted. But what happens is that as we increase our frequency, we're going to start bypassing more and more of these capacitors. So these capacitors start looking more and more like short circuits. And if we go all the way to 100 kilohertz, we're operating at peak gain here. So this is our gain of 48 volts, okay? So 48 volts per volt. So we're operating in our peak gain. If we drop it down to 10 kilohertz, then these capacitors, like we said, are going to start having these undesired effects. We're going to have to start really thinking about these circuits. Now, if I change this to where maybe it goes a little bit further, so if I make it go to 100 mega ohms, what you'll see is that it starts dropping down, and it starts dropping down considerably, okay? So past about, let's see, that looks like 60 megahertz to me. We're not going to be getting any gain at all, okay? And the reason for that is because, like I said, these MOSFETs are not 100% ideal. So there's capacitors everywhere in these MOSFETs. So whenever you start getting into really high frequency, you either have to use a MOSFET specifically designed for it, which this one is not, or you have to start being really, really creative with your amplifier design, okay? So this is a brief introduction to these MOSFETs as amplifiers. We got to look at one type, the common source amplifier. We analyzed it, saw how we can get the gain, how we can use the hybrid pi model, and all these other sorts of things, how we bias the MOSFET, how we bias it correctly and get the correct voltages so we have maximum headroom. And then you also got a sneak peek at how you can actually simulate them in an amplifier. So I really encourage you to try and make this simulation for yourself, because you're going to learn quite a bit, especially probing around this MOSFET, seeing how everything affects the gain, how everything affects the frequency response and things like that. It's going to give you a lot of insight into how these amplifiers work. If you have questions, please feel free to leave them in the comment section below. If you like this content, give me a thumbs up and subscribe to see more. It really does keep me super highly motivated and really makes me want to churn more videos out as quick as possible. Other than that, thank you guys for watching, and I will see you next time.